Very good afternoon to all. It is our great pleasure to see you all at the second session of the day one of International Conference on Advances in Materials and Manufacturing. This happens under Knowledge 4.0 webinar series, which is one of the unique and distinct initiative of Chennai Institute of Technology under the guidance of our Honorable Chairman, Sri P. Sriram, who is one of the well-known first-generation entrepreneur, industrialist, Managing Director of MK Group of Companies. Under Knowledge 4.0, we have been conducting webinar series such as Technical Webinar Series, Research Webinar Series, Career Guidance Webinar Series, Innovative Talk Webinar Series, and Aluminium Webinar Series. This Knowledge 4.0 webinar series is being conducted to enhance the knowledge of faculty members, researchers, and students community. And so far, we are very proud to say we have conducted more than 150 webinars during this lockdown period by keeping the motto as lockdown is only for the worldwide and it is not limited for learning. So by keeping this motto, we have been conducting the webinars. So far, as I said, 150 webinars have been conducted. Today we have Dr.Supriyo Ganguly, known person for welding and additive manufacturing from the Cranfield University, to share the session. It is our proud to welcome you for this wonderful session, sir. Welcome you for this wonderful session, sir.
Thank you.
Chennai Institute of Technology was established in 2010 by our Honorable Chairman, Sri P. Sriram. Today, our institute is being within top 10 among all other private engineering colleges in Tamil Nadu. It is my great pleasure to welcome you, all the participants, and our expert, Dr. Supriyo Ganguly, sir. And now I request Swapna Sai to welcome our introduce our expert, Dr. Supriyo Ganguly, sir.
Good afternoon, everyone. Myself, Swapna Sai, pursuing second year Mechanical Engineering at Chennai Institute of Technology. Dr. Supriyo Ganguly, Professor at Cranfield University, United Kingdom. He graduated from Bengal Engineering College, Calcutta University as a metallurgical engineer in 1994. Dr. Ganguly got his PhD thesis in residual stress measurement of welded aerospace alloys using neutron and synchrotron X-ray diffraction process from the Open University in 2004. After his graduation, he worked in Usha Martin Industries Limited for 3 years and Tata Steel for 7 years as a metallurgist, where he worked in iron and steel making, rolling, and then as a technologist in the area of product and process development. His areas of research interest includes standardization of residual stress measurement using neutron diffraction, understanding creep response in weld metal and heat affected zone of alloys used in high temperature application, and fracture mechanics. He has published more than 100 journal articles with high impact factors. We welcome you, sir.
Thanks, Swapna. Thank everyone who are interested in knowing a bit more about the advances in materials and manufacturing. First of all, let me clear. Am I clear?
Yes, sir. You are audible, sir.
Yeah. Thank you very much. Yeah. So, what I will do in this session is to basically share with you what we are doing in the area of manufacturing. So that the main purpose of this particular presentation would be to introduce you to Cranfield University, and then I will introduce you to our Welding, Engineering and Laser Processing Center. I would like to show that what kind of facility we have, and you will see that the scale of the facility, and which will allow us to easily scale up any research that we do here up to industrial satisfaction. So most of our work are basically sponsored by industries, and also we have a big portfolio of UK research institutes such as Engineering and Physical Sciences Research Council and everything. So today in advanced manufacturing area, I will be speaking on wire plus arc additive manufacture, which is as you all know, 3D printing. Probably it is the hot topic of the time, and wire plus arc additive manufacture is one of the specific type of 3D printing. So I will explain on that. I will talk a little bit on laser and laser plus arc processes that on which we work, and also on how structural integrity matters. So at the end you will see like all the different manufacturing processes are basically focused towards obtaining a very cost-effective product. The cost-effective product would come from saving of material, and B, by increasing the durability, the structural integrity of a component or of a functional structure.
Sir, you are sharing your session, PPT, sir.
Sorry?
Have you started to share your PPT?
It is already shared. No?
Please do it once, sir. Please do it once.
Okay.
Yes, sir.
Can you see now?
Yes, sir. You can open your presentation, sir. You can open your presentation. Yes, sir. You can maximize it. Yes, sir. Please, you can go ahead, sir.
So shall I restart or can I continue from here?
You can no problem. Only you started, so you can.
It's just So, yes. So the basic thing is, I will go back to the slide 1. It is basically this, which is just to talk about the advances in materials and manufacturing that we are doing at Cranfield, and this is basically what I was talking about. So today's I will share with you the research that we do in the area of advanced manufacturing in our center, and that will be on wear plus arc additive manufacture. So this is one of the very major strand of our research, and about 70 to 80% of our revenues are come from this now, and this is a hugely focused area of research in manufacturing all over the globe. I will talk about laser and laser plus arc processes. I did several projects in this area, particularly in the area of laser plus arc processes, and also now I'm having some work going on in the area of application of laser for e-mobility applications. I mean, joining of e-vehicle batteries and all those kind of stuff. And I will talk a little bit about the structural integrity, which is also a major aspect of advanced manufacturing, because at the end of the day, the whole manufacturing is basically focused on how to reduce the cost of a component, be it by saving of material or by increasing the overall life cycle of a component, and that is where the advancement in manufacturing lies. So I will speak on those aspects. So first I will go a brief about where are we. So we are in United Kingdom. As you can see, we are separated by, at the moment, by about 5,000 miles. And within United Kingdom, we are located about 50 miles north of London. And you can see our nearest airport is the Luton Airport. And Heathrow is like 50 miles south of us, south from here. So a little introduction of the Cranfield University. So Cranfield University was basically a Royal Air Force base during the Second World War. And by the end of the war, it was realized that there is so much of information that was generated during that period that it would be a sheer waste if everything is wound up. So College of Aeronautics came up in 1946. In 1969, Cranfield Institute of Technology formed, which can give university level degrees. And from 1993, Cranfield University formed. So I will say a little bit more about our main research activities. So we are UK's #1 university in aerospace engineering and technology postgraduate creation. We are world #10 in customized executive education. In mechanical, aeronautical, and manufacturing engineering, we are ranked among the top 40 places. And our unique facilities include Aerospace Integration Research Center, Crash Impact Center, Secure Site, National Wind Tunnel Facilities, National Reference Center for Soils, Facility for Airborne Atmospheric Measurements. So you can see here a bird's eye view of Cranfield University as it is now, and you can see this huge runway, which is about, I think, 1.2 kilometers long, and we are creating about 4,500 postgraduates. We are a postgraduate university, and our main area of our main focus is in applied research, and that you will see in my next slides. So our distinctive strengths, if you come to the left hand side, you will see these are the different themes which is distributed in 4 schools. So aerospace, defense and security, energy and power, environment and agri-food, school of management, manufacturing, transport system and water. And I am part of the manufacturing team, and furthermore I am part of the Welding, Engineering and Laser Processing Center. So this is a brief video showing about Cranfield University.
As an exclusively postgraduate university, we take learning to new heights in technology and management. We award over 5% of the UK's engineering and technology PhDs every year. 81% of our research is classed as world-leading. Our academics find solutions to global challenges. Our graduates leave ready to launch into high-flying careers. That's why we rank in the UK top 5 for both commercial research and professional development. Everything we do is in partnership, whether it's with individuals, business, government, or industry. Here at Cranfield, we like to aim high across technology and management. Our work reveals new horizons, and we create the leaders to get there.
So this is a brief introduction about Cranfield, and now I will talk about our center, which is Welding, Engineering and Laser Processing Center. In the red rectangle in the left hand side image, you can see where the size of our building. It is founded in 1961. It was not located here in 1961, but it was founded in 1961. And at the moment, we have over 600 alumni with MScs and PhDs. We have about 8 academic staff. Actually, we are increasing in number every year almost. We have about 3 technicians. Normally, we have about 10 to 12 postgraduate fellows, about 15 to 20 research students, PhD students, and we run a master's course, or rather we run 2 master's courses now, one on welding engineering and the other on metal additive manufacturing. And we normally have about 16 full-time equivalent students in welding, and about last year the metal additive manufacturing course started, and it has about 10 full-time equivalent students. So I will give you a brief view of our lab. So you can see now we are located. So this is done by a student using his drone basically. So you can see the size of our facilities, which I was talking about actually. So it is located over 700 square meter, and as a result you can really do research in a scale where industries feel comfortable with, so the technology transfer is rather straightforward. So we have robotic welding mostly. We don't have any manual welding, and what we basically seek to achieve is to understand the welding process. So we have all the instrumentation facilities, residual stress measurement facilities on how to characterize welds and everything. And these enclosures are made, as you can see now here, it's like a tent. So we fill this bubble with say argon or something, to make inert environment for manufacturing of say additive build parts like say titanium and stuff. So I will talk about wire plus arc additive manufacturing now. And as you can see, so this is a conventional way of manufacture. So where you have a billet and you scoop out the component from it, whereas when we talk about additive, it will be like this. So it is layer by layer deposition. I am sure you all know about this, and we are basically in the right hand side of this image, where you can clearly see we use an arc as a power source, be TIG, MIG, and plasma. This is the major arc, but also we use laser and we use wire. So this is a very clean process because we use wire, because when you use powder, the safety requirements and the process can become much more difficult to control, whereas wire is much cheaper, much more property-wise more consistent and everything. And this process we termed as wire plus arc additive manufacture. So I will just give you some snapshots of what is a powder-based processes. As you can see that in the powder-based process, you put on powder, and this is a powder bed process. And then there will be a laser which will scan the powder or scan the shape in the powder, and the stage will go down, and you will sinter the powders together by the help of a laser or a power source. In this case, it is a laser. And at the end, as the bed goes down, you manufacture the component. Once the component is manufactured, it is then cleaned, because there will be powder that will be clinging onto the surface, and you will find the component that is actually sintered inside this superficial layers or superficial powders. So this process is an extremely important process, and wire plus arc additive manufacture is a different process in terms of, I'll just go to the next slide when it will be cleared. Yeah, so this is wire plus arc additive manufacture. So in the previous process, you have seen powder and laser. So they are very good to create very complicated geometries, and the deposition rate in that process is very low. In wire plus arc additive manufacture and near net shape, the previous one, so it is very close to the actual shape and the dimension of the component. Whereas in wire plus arc additive manufacture, you see on the right hand side, the ongoing video is basically you're feeding a titanium wire in a welding arc. On the left hand side, it is an animated image. However, on the right hand side, or on the bottom, you can see the real component. So this is a landing gear box made of titanium, and as you can imagine, so creating this type of component in a laser plus powder system will be very, very difficult, because the size of the component is in meter scale rather than millimeter scale, and the crystallinity requirement, I mean the dimensional resolution that you need, is not as high as that. So you can machine this and make your component. So why use additive manufacture for production of large parts? So this video shows that what is the importance. So you have seen at the beginning, there's a large billet which was then scooped out to form this part. When it comes to expensive alloys such as titanium, then the cost is prohibitive, because you are losing serious amount of metal. We call it buy to fly ratio. So how much you are buying and how much is actually flying. And if you see in this particular example, there is a huge loss of metal because you are machining out, and the scrap titanium is as you can see, about 2 orders of magnitude cheaper than the titanium billet. So to reduce cost and increase lead time is the specific business case for wire plus arc additive manufacture. So these are the major business drivers: reduce lead and response time, logistical simplicity, supply chain innovation in component design, reduce weight, lighter and more durable, material saving, improve sustainability and recyclability. So these are the main business driver for wire plus arc additive manufacture. Now, there are several attributes which is shown in this spider diagram, like complexity, accuracy, cost saving, material utilization, mechanical properties, post-processing requirements, platform flexibility, part size and all. And you can see there are different additive manufacturing processes were compared: powder blade, blown powder, laser and wire, WAAM, and high deposition resistance, which is the CIT process. Now you can see WAAM is placed in a very nice manner for many of the things, particularly cost saving, material utilization, mechanical properties, post-processing requirements. There are many of them, they are much low. I mean, the criteria for selection of this process is much higher. And the main important thing is buy to fly ratio. So when it comes to buy to fly ratio, it is in WAAM, in case of WAAM, it will be quite, I mean, you can easily achieve something like 3 to 1. So which basically means 3 kilos you're buying and 1 kilo is ready to fly. So which makes this process incredibly lucrative for businesses. And although powder bed and all those things are very good to create very fine crystalline structure, the deposition rate is not as high, and as a result the cost of production could be much higher. So this is a process of shaped metal deposition which I was trying to show here. So we started this process quite a while back, and as you see, this is the concept of the component, and then a CAD drawing was made and layer by layer manufacturing was done to create the component. So this is material is Inconel, number of layers 144, deposition 2.44 hours. And since then, for the last 18 years, 19 years, we are working tirelessly on this particular technology, manufacturing technology, and now it has gone to a level where you can really do lots of different things. So this is a airframe, titanium airframe. So as you can see in this particular frame, so we keep this in our center just to show the different types of deposition strategies, the complexities that you can use. So few of the layers were made with single pass, few were laid with parallel passes, few were laid with oscillatory passes, and so these are the different difficulties that are different processes that you can use for creating a large part. So which process to use? So there are processes like MIG and CMT. So you see this is the aluminum spar developed by this, and then there are processes as plasma. So there are different types of processes that you can use. All have different attributes, like say MIG or CMT gives you very high build rate, synergy between current voltage and wire feed speed, which basically means in a MIG process you really don't select lots of different parameters. What you select is basically the wire feed speed. Okay, whereas in case of plasma, you have individual control on current voltage, and that makes plasma a really very attractive process for wire plus arc additive manufacture, because as you will see, like there are different types of shapes that you need to form, and your deposition rate needs to be changed even within the same layer, and as a result you need to have individual control. So for specific parts, if they are straightforward, you can go for a MIG process. If it is complicated and the geometry requirements are complex, probably you have to go for plasma. Of course, plasma has less efficiency, i.e. deposition rate. However, it is a very clean and very controlled and nice process. This is a thing just to show you, just to make impress on you that how difficult is this process. So in a steady state, as you can see, all is very good. But when it comes to, as you can see, the weld pool strings when it comes to a junction. So you will see that many people can develop a wall, a single wall, a simple wall is quite straightforward. But when it comes to very complex equipment or very complex component, it can be incredibly complicated. And this particular video is showing that how the fusion zone strings when it comes to the junction. And as it comes to the junction and its strings, what it basically means that you have probabilities of forming lots of different types of defects in this area. And as a manufacturer, what is required or research is mainly directed now to understand how you can overcome this kind of obstacles in order to make a defect-free component by using this process. Okay. Controlling the composition using multiple feeds. So this is one of the design flexibility or material design flexibility that is offered by the WAAM process. So you can have multi-wire in an arc. This is called tandem welding, or many people can say different names, but you can have different grades of wire going into the same pool, and in that, thus you can really control the weld pool composition, and thus you can control the solidification path that the weld pool will follow, and thereby reducing chances of cracking and stuff. So this is a particular work that was done a few years back, and where it was shown that how the copper and magnesium ratio within the weld pool was controlled in order to achieve solidification free welds actually. But the same principle can be transferred for additive manufacture. You can add more than 2 wires depending upon the composition and the melting point. You have to make sure that the heat is sufficiently high so that 3 wires can be melted and accommodated in the weld pool. This is another example of creating a composite part. So this is for a brake disc project that we did few years back, and here you can see that the weld bead that is shown in the middle picture has tungsten carbide embedded in it. So how we have done this? It is shown in the left. It is a TIG arc, and then you feed the wire from this shaped wire feeder, and you blow powder inside it so as to make a composite structure. So basically this was made for a brake pad application in order to create a brake pad which has very high thermal conductivity, because when brake pad is engaged against a brake disc, the temperature rises rapidly at the interface, and then what you need is basically the heat to be conducted away so that it doesn't affect the integrity, and at the same time you need sufficient abrasion resistance. So this kind of composite structures are basically created with powder, which is tungsten carbide, and wire and steel wire to for such functional applications. Controlling the composition, mixing of materials. So as you can imagine, you can have bimetallic structures quite easily. This is an example of iron and copper, and if you're careful, you can see there at the top there is a honeycomb type structure which is shown at the top. So these are all different design modifications that you can do. You can apply different material, different alloys. So what I'm trying to say is that previously with the traditional processes, the designers are basically limited by what processes are available. Now the advent of WAAM is really pushing that limit. So now it is possible to make topologically optimized designs and then produce the component by using WAAM or such processes. So there are multiple examples of having mixed material. Control of properties. So this is an important thing which I think you should know. WAAM as a process is very good, but as it a process which depends on solidifying of molten material, it will form very columnar dendritic grain structure, which is exemplified on the left hand side macro image. This one, you can see the grains which are going vertically down. This is near the substrate, and this is the deposits. Now we invented a process of cold rolling, by which when we deposit, we can roll a layer, and doing that, what you basically do while rolling the layer, you induce cold straining in it. The rolling of the layer is done at a lower temperature. Lower the recrystallization temperature of this alloy. So you deposit a pass, wait for some time, and do this rolling, and you induce cold straining. So when you deposit the next pass, what will happen? You're going to redistribute the strain. So basically, you're not creating a recrystallized structure, or you may create a recrystallized structure, but you are obviously creating a kind of a high angle grain boundaries as compared to the columnar dendritic grains. So when you do this, what will happen basically is shown in the mechanical testing results. As you can see here, directionality, which basically means anisotropy. So in different directions, you have different properties if you have a columnar grain, and you can see this filled in black and this open cycle black. They are quite widely different in terms of proof strength and tensile strength. Whereas when you roll, these are the different rolling loads that are applied, and you can see here they are almost merged. So you don't have any directionality anymore, and the properties have increased tremendously. So this black triangle is showing the plate, which is a wrought alloy. So you can create properties in the deposit which is similar strength or even higher strength than the wrought version of that particular alloy. Now, rolling, as you can imagine, can be quite complicated because it needs a large frame to put the rolling load onto the structure, and for doing rolling on complex shapes can be quite difficult. It's quite impossible. So what you do here is a machine hammer peening. So this is a fantastic tool which does the same thing as rolling, but it is much more flexible, and we are studying this at the moment. As you can see here, so we deposit a layer, and then there is the machine hammer peening tool that comes into the picture, and then it does the machine hammer peening. Okay, so it is basically done exactly the same thing as your not sure why this is not starting. Yeah. So you're depositing, and then you're bringing the machine hammer peening tool, to peen, and then you deposit one thing. So this is the peening process that is happening. Okay. So what happens when you peen? You form compressive stresses, and when the next pass is deposited, you basically manage to get a sort of recrystallized layer. So a work was done on titanium 64, which is one of the main alloy which we produced by WAAM process. So as you can see here on the left, it is the columnar grains. On the next picture is interlayer machine hammer peened, which gives you this is the BSD map, which is following that, and it gives you complete high angle grain boundaries, as you can see, with very nice structure. And And this is the strain map and the inverse pole figure of the build that is shown. So average grain size reduced, the strain depth was measured, up to what depth the machine hammer peening is inducing the strain, because as I said, it is done in cold condition, and it will and you have to have a proportion of the layer height and the straining that you can induce. Property wise, once again, just concentrate on these green ones here. The green ones here is the as deposited ones, which are much lower, and the rest are peened. And you can see that the property has moved up substantially, both in terms of UTS and YS. So this is some more examples of doing a hardness map and showing that that when you peen, your hardness goes up, which basically indicates that it is strain hardened. So this is quite natural, and because of that, you're getting the recrystallization after laying the next or the following bed. Okay, so these are the things that we are starting in WAAM plus Additive Manufacture. I will now share you some of my work in the area of application of lasering joining. So specific advantages of laser. So why you use laser in advanced manufacturing? It can produce very high power density. So the spot size over which a laser welds can be a few micrometer to a few millimeter, and therefore you have very high flexibility in application of energy density, which is the third point. It can create different welding modes. I'm sure you have heard about the terms like keyhole welding, conduction welding, and all these can be done very flexibly using a laser. You have very high spatial and temporal resolution, which basically means where you will apply the heat, you can control to a very high degree, and temporal resolution means for pulse laser, you can have very accurate pulse shapes. So the application of the energy with respect to cycle time can be controlled very easily and very accurately. Higher power density generally gives you lower heat input, thereby lower distortion, higher productivity, and all this. So as I said in the beginning, I will talk a little bit on the laser plus hybrid process. So why you use laser? So A, for productivity, B, for very accurate welding, so which is like in e-mobility and places we are joining copper which are say 0.5 millimeter thin, 1 millimeter thickness, and therefore you need very accurate heat source. For that is used. The other way, the other important thing, laser for high or thicker structures is laser plus arc processes. So you can see laser plus arc hybrid welding has the potential of faster welding with a high heat input and higher gap bridging capability. Lower dilution ratio is often necessary to impart the necessary strength and metallurgical characteristics in a joint. So we have done a feasibility study using laser and laser plus arc hybrid process in 2G welding configuration with an aim to optimize the productivity. So you will see in the next slide. So this is the setup. So this is the pipeline that we are welding. So this is 2G configuration. Basically the pipe is vertical and the welding torch is coming horizontally. And some details are given here, which is not very important at this stage. The most important thing is this one. So when you do laser welding, if the process parameters are not controlled, what you do, you create a molten pool at the bottom, as you can see here. Follow my mouse, which is done by melting of the parent alloys, and the arc process deposits the metal which remains in the top and it didn't penetrate. So this is not good, because these two part can be create a very highly graded structure. So this particular experiment was done with duplex steel, actually, just putting chromium as a signature element to understand the performance or the response of the different arc and welding powers, arc and laser power sources for creating a proper homogeneous structure. So on the right hand side, I'm showing you the bevel configuration. So this is the 12 millimeter is the depth of the bevel. And now you can see here there is huge segregation of metal. So basically arc and laser power, they don't at all coupled with each other. So now we increase the wear feed speed. So basically, which means we use the arc, increase the arc energy. Now arc energy is shown here, as you can see, from 4.48, now it is 6.69. And slowly as we increase, you can clearly see that how the mixings are accomplished. So now, as you can see, like this process using laser plus arc, you create a completely homogenized structure, a completely homogeneous weld metal, which will be as good as it can be if you use a normal arc process. So this a study that was done. So this is for the root pass welding, and these two macros on the right is showing basically a single pass hybrid laser mix. So this is basically almost 12.5 to 13 millimeter, and you can see you can create a complete proper weld in couple of passes. Whereas if you just use MIG, it will take like 10 passes to create such kind of structure. So the productivity is improved by miles, basically. So other research areas at Cranfield at the moment, we are seeking application of laser in dissimilar joining. So if you're interested, I can show you later on what is a dissimilar joint, and some specific research that we did on transportation, nuclear power, marine structures, joining of functional components for e-mobility applications. So this is the hot topic of the day, e-mobility. So where we are joining copper and different dissimilar configurations like copper and aluminium, copper and stainless steel, and similarly aluminium and different dissimilar configurations. So aluminium and then aluminium with copper. So we have done a huge study in these areas. Now we'll talk a little bit on the structural integrity by laser peening process. So we have a laser which can peen, which basically means this is basically the peening process in a schematic. So you can see on the picture A, there is a laser pulse which comes and hit the surface of the metal, and then there is an overlay of transparent overlay of water here. And sometimes people use what we call an ablative layer. Sometimes people do not use an ablative layer. So because when you don't use, the metal itself will vaporize. So you bring this at a very high power density in the tune of say 4 gigawatt per centimeter square for aluminium, I mean. So then you heat it very hard, the aluminium vaporizes, it will try to escape the surface, but this water will prevent it from escaping. So what will in turn it will do? It will send a shock wave inside the workpiece, and the shock wave will help you in creating a residual stress field by elastic pushback. And this residual stress field will be compressive in nature. And this compressive stress field is very good for prevention of fatigue crack propagation and opening. Why? Because when you have a compressive stress, then crack doesn't open. Crack opens under tensile stress. And so the compressive stress, when superimposed, say you generate a compressive stress of minus 200 megapascal. Now in your actual application, your tensile stress that it will be subjected to is say 250 megapascal. So then basically actually the stress that is acting on it is 50 megapascal. So you are reduced the magnitude of stress, and you can see here that you create a very large compressive stress. But remember, there will be a balancing tensile stress. But the tensile stress, balancing tensile stress, if it is created in a region which is not affected by this, by the crack propagation, then you really don't matter. So when you create such process, you have to be a bit mindful about how the balancing residual stress will be created. So this particular project, we worked on a Airbus component, which is a fuselage, and we tried to resist the fatigue crack growth by laser peening. So the alloy was aluminum 2024 T351, which is a very standard alloy. And you can see here the grain structure, and on the top the galvanized layer of aluminum. So these are the properties that were shown. This is nothing new. So this is what is new. So what we did, we laser pin. So these are structural joints, so which are basically bolted. Now from this, in this area, the main fatigue crack starts, okay, from these bolted areas. And why is it so? Because there are a few mechanisms. So one of them is the abrasion that results in a crack propagation. And also it is subjected to fatigue. So fatigue and abrasion are the two major failure mechanisms that are active on these holes. So now this is shown the jointing mechanism. So we pin both the surfaces and we do a batch pinning is shown here, and this is the array of holes and they are pinned. So always people will find that the failure will happen at the top row or at the bottom row. The middle row was never affected by this process. So in order to make this thing strengthening, in order to strengthen this part, we only pinned the top and the bottom rows. So these are some examples. So there are different types of pinning that we studied. So we call this stripe and we call this batch. And as you can see, the pinning process creates a good amount of residual stress. This is the compressive stress, which is balanced by tensile far away in the plate. And this plate is 2.3 millimeter thick, and the crack will propagate through the thickness. So the main target is to prevent the crack propagation through the thickness. And you can see here all the different types of stress profile that we obtained. So just keep an eye on this PB configuration, which gives you a maximum compressive stress of minus 270 and minus 174. We will see that this particular pinning is a much more helpful pinning, and so this is the pinning results of the P samples. This is the work that was this is my specific areas of expertise. So I use a lot of neutron and synchrotron in order to understand the stress state. As you can see here, the blue bit is basically meaning compressive stress. So both the stripe and the batch configurations created tensile stresses. Now if you see one thing very carefully, here it is, because it is stripe, the entire thing is compressive along the whole of the length, whole of the width, which is really not required, because it means the balancing tensile is forming somewhere here in the middle of the specimen. Whereas when you are patch, then basically you create the compressive stresses around the holes, but in between two patches the balancing stress field is forming. So you see, this particular design is more useful because crack will never start from here, because crack will start somewhere from here, and you are creating a large compressive stress around that, but crack will propagate like through the thickness, and therefore you are minimizing the tensile here because your balancing tensile is forming here. So these are the things that you need to understand when you design a particular component for a particular application. So this is an example. So the green one is the patch one. As you can see, around the hole there is a good compression, but in case of S sample there is compression, but because this measurement is through the thickness and there is a balancing tensile in the middle, the average values is showing as 0. So this is basically the overall stress configuration. And you can see here the black one is the stripe one, S1, which has very large tensile core, which basically means when the crack starts, then once it reaches here, it will tear through it quite quickly. Now I will explain this in this one. You will see here. So BL stands for base level. So base level versus S samples. As you can see here, the S samples are the stripes. So you can see the life improvement factor that you achieve using stripe is maximum 1.52. Whereas in P samples batch, the life improvement factor you achieve is almost 3.54. So 4 times life improvement you can get when you did a good pinning in this configuration. So this type of studies are actually showing how you can improve the life of a component, and thereby you can save, say, material and do a much thinner design of a structure. So this is the previous result shown in a graphical form, basically. And when we measure the striation, the fatigue striation spacing in ACM, because striation spacing basically give you the crack propagation rate, the DADM. Now, when we measure this, we clearly see. So please follow this line, this particular red line. Here, there is a lot of data in this particular graph. Some are showing the residual stress. The crack propagation or the striation spacing is basically done by this reddish triangle. Now you see here it is quite low, and then at the middle it is high because it is tensile at the middle, and then it once again becomes low. So this clearly shows that that the fatigue crack propagation rate is reduced significantly by the pinning process. Now these are life improvement factors. So always a question like how the life is improved. So whether the life is improved by reducing the crack propagation, or whether the life is improved by delaying the crack incubation or the crack initiation period. So you can see here the life improvement factor is about 1.3 or 30 times or 30% life is improved when you have through extension and crack growth. But when you have 3.54 times of life improvement, which basically means that the majority of the time the crack is closed, and therefore you have less, you have such high life. So the effect of compressive residual stress on life extension is mostly by delaying the initiation. So all these studies you can do by understanding the crack propagation and the effect of residual stress and everything. And modern days quantitative characterization facilities like neutron, synchrotron, high resolution ACNs, they will allow you to understand everything. And what you need to do is to understand the mechanism or the underpinning science, and then apply it judiciously in improving life, in creating new manufacturing processes. So this is my last slide. So my thoughts are, the main purpose of research in manufacturing technology is to reduce cost by, there are basically two methods: reduction of material consumption and reduction in overall life cycle. So even if the manufacturing cost is high, but the life cycle of a component is increased by 10 times, then the overall life cycle cost is much lower. So people are ready to pay once they understand what is the importance of it. The recent advances in design technology would allow a complete topographic optimization of a component. Therefore, now our job is to adopt the principle of design-led manufacturing. So it is not the designers are tied up with the manufacturing process. The manufacturing process should be freed up, and designers should do topographic optimization of components using multi-material, using application of anything, basically functional, structural components. And as a manufacturer, our main aim should be to use all the latest advancement like laser, additive manufacture, peening, and all the different processes available under the sky in order to generate those components, the topologically optimized components, in a cost-effective manner. And that will be the future of advanced manufacturing, as I understand. So thank you very much for listening to me. If you have any question, please let me know.
Yes, sir. Yes, sir. Thank you, sir. Thank you so much. Thank you so much for sharing your knowledge. It was a nice presentation. and he has given a lot of information on additive manufacturing, wire additive manufacturing. I hope this will be highly useful to the researchers, those are participating, and certainly their research knowledge might have been enhanced, and it will help them to get into further research. Thank you, sir. Thank you so much.
You're welcome. Yeah.
Let me.
I'm slightly late actually. It is almost.
No problem, sir. No problem, sir. Sir, Mr. Chandramouli Ramaswamy had asked one question.
Yes.
Sir, is it possible to perform laser peening on gas turbine plates?
Absolutely. So the whole point of laser peening is actually laser peening is in operation for some of the very high-end applications like gas turbine blades, in particularly in aircrafts, and therefore it is possible, and it is used for very niche applications at the moment, like as you said, gas turbine blades. But our target is to make it more cost effective. At the moment, the cost of a laser which does such peening is basically quite high. So the pulse energy that is required for such kind of laser performance is in like more than 1 joule. So one of the major supplier of laser peening is called I forgot their name. They're in MIC, Metal Improvement Corporation. And if you see the laser they use are quite, the power is quite high. The pulse energy is quite high. It is close to, as I understand, 10 joules, so which is extremely high and it is expensive. So one of my research activity is to create peening by smaller pulse energy. So like I have a laser which has 800 millijoule, and I did some work a few days back for a pump manufacturer. So yes, to answer your question, yes, it can be done, and it can really increase like fatigue and also creep fatigue. So all these different critical service conditions can be dealt very well by laser peening.
Yes, sir. Thank you, sir. Thank you so much, sir. Sir, Dr. N. Karshavardhana had asked one question. Sir, is it possible to develop magnesium alloy using WAAM process? What are the difficulties, sir?
What alloy?
Is it possible to manufacture magnesium alloy using WAAM?
Mechanism alloy?
Magnesium alloy, yes, sir. Magnesium.
Oh, magnesium. Okay. Yes. Magnesium is possible. Of course, it is possible. We have done some work, I think, using copper magnesium wire, and yes, we have deposited some work, but there are few difficulties with magnesium. Is as you know, it is quite flammable, so you have to take proper precaution. And secondly, magnesium vapors are very dangerous for human health. So you need to really create an enclosure and stuff in order to do properly these magnesium based alloys.
Yes, sir. Yes, sir. Thank you, sir. Thank you. And another one question we will take, sir. One question asked by Alur Manoj. So he wants some tips from you, sir. Could you please recommend some few tips for our students, those who can learn and can approach you to join in your renowned research group?
Okay, so joining in my research group is possible. Like all our positions are advertised. You see, there are. So first of all, you can do a master's in our group, and if you perform well and stuff, then obviously there is a possibility that you can get a PhD. Now, when to get a PhD, there are two ways actually. So if the grant is from research council, then often the grants are mainly for UK students. However, if the grant is from an industry, then it is possible to have the grant for anyone actually, in university student and all. So that is one way of joining to do a PhD research with us. The other way, as I was discussing with you, Professor Dinakaran, is to have a grant or something against a call in against India UK calls, you know. So India UK calls are always there time to time. We call it Newton Fund, and also the grant that I have is Royal Academy of Engineering. So there are always such grants available, and mainly they allow for researcher transfer. So like students from VIT came here to do some work with us. So what we can do, we can apply for a grant, and if we are successful, then we can use that money for some people to come and visit here, stay here for 3 months, and learn some of the technologies, techniques, you know, to do work. Also, you can come for internship, maybe a possibility. That is one of the area that we are trying to open up slowly. If you do an internship with us, then and then further, if you come for a master's program, then I mean, your cost for internship will be deducted from the master's program that we are trying to create.
Yes, sir. Thank you, sir. Thank you, sir.
Yeah.
Sir, thank you so much, sir. Can you come out from this one? Can you share?
Okay.
Can you? Sir, thank you.
Okay.
Thank you so much, sir. Thank you so much.
Thank you very much. Yeah. Thanks very much for having me. And I hope when this Corona thing goes away, then we can have a good chat at Chennai, or if you come here, you're always welcome to visit us. Okay.
Yes, sir. Yes, sir.
So yeah.
Thank you, sir. In the summer occasions.
Thank you. Very nice meeting you all. I hope you enjoyed the talk.
Yes, sir. Yes, sir. Everyone might have enjoyed, sir. Thank you, sir. Thank you, sir.
Okay.
Bye, sir. Dear participant, thank you so much. It was a nice lecture on additive manufacturing. He is one of the well-known person in additive manufacturing and laser welding. And so tomorrow the lecture will be by 10 o'clock by Dr. Satyanarayana from NIT Tiruchirappalli, and the next session will be on tomorrow. Fourth session. Day 2, fourth session will be by Dr. B. Balasubramaniam, Annamalai University, at 3 p.m. tomorrow at 3 p.m. evening. Okay. So, as he requested, no feedback link will be shared now in all the sessions. Okay, so finally I will share the feedback, and I will send the certificate also. Along with the certificate, feedback form will also be sent. And those who did not join in WhatsApp group, please do it. So which will be useful to get the communication in very fast rate. Okay. So thank you. If anything else, you can reach through my WhatsApp number. We'll meet tomorrow.